Okay, in today's session, we will start with electrical analogy of radiation. Within 5 minutes, I will revise whatever we have discussed till now, and then we'll start with this new topic, which is electrical analogy of radiation. Already you have seen electrical analogy of conduction. Okay, anyway, till now we have seen four different laws of radiation, right? Like Planck's law, Kirchhoff's law, Stephen Boltzmann's law, Wayne's displacement law. Then in last lecture, we have seen the concept of view factor, and we have seen how to apply that view factor to work out numericals. In today's session, we will see electrical analogy of radiation, right? Now see, in case of radiation, there are two resistances. I repeat, in case of radiation, there are two resistances. Which are those? One is surface resistance and second is shape resistance. So there are two resistances in radiation. One is surface resistance and second is shape resistance. What is surface resistance? The resistance offered to flow of heat by radiation at the surface itself is called as surface resistance. It is given by the formula 1 minus emissivity upon area into emissivity. See, these formulas are very simple. Surface resistance is 1 minus emissivity upon area into emissivity. Already in last lecture, we have discussed what is emissivity, what are the appropriate values of emissivity, right? Okay. So the first resistance is surface resistance. It is the resistance offered to emission of heat or resistance offered to absorption of heat. I will explain that later on while we'll discuss electrical analogy. Before electrical analogy, let us understand what are the resistances in case of radiation. So there are two resistances in case of radiation. The first one is surface resistance. What is surface resistance? The resistance offered to the flow of heat, right, by radiation at the surface itself for absorption of heat or emission of heat is called as surface resistance. Why it is called as surface resistance? Because it is offered at the surface. It is given by 1 minus emissivity upon area into emissivity, right? Now, before starting this, let me tell you where you will apply electrical analogy of radiation. Wherever the heat flow is by radiation. See, being engineering students, we have to apply the laws of conduction, convection, and radiation, or the concepts of conduction, convection, and radiation. I will just take your 2 minutes. See, if you are designing insulation for a steel pipe, right? Let's say steam is flowing through that steel pipe and you are designing insulation. Being engineer, what you have to find out? You have to find out that thickness of insulation so that the heat loss will get reduced. Or it may be the other case, like you will be given thickness of the insulation and you will be supposed to find how much rate of heat loss is decreased because of that insulation, right? So this is application of conduction, because through insulation the heat transfer will be by conduction. If you take example of convection, let's say you are designing a shell and tube heat exchanger and you have to design length of the tube, right? How will you design that? In that case, the heat transfer is by convection. So applying the fundamentals of convection, applying Newton's law of cooling, applying the other equations like Nusselt number, Reynolds number is there, Prandtl number is there, you will work out the dimension L, length of the tube, or you will find number of tubes required. You will design the passage of heat flow, how that heat will flow, right? So you will design that heat exchanger by using the concepts of convection. Similarly, radiation, where you will apply radiation, let's take example of annealing treatment process of steel. Now in that furnace, you have to increase the temperature of steel from 30 degrees Celsius to 560 degrees Celsius using electrical heaters. So the heat is flowing from electrical heaters to steel plate. Now that heat is flowing by radiation. So when you have to design the rate of heat transfer, or let's say the other case, you have to design velocity of steel so that much heat is transferred. You have to design the length of furnace. In all these cases, you will apply the fundamentals of radiation, right? Okay, we are discussing electrical analogy of radiation. In electrical analogy of radiation, we have to consider two resistances. They are, first one is surface resistance, which is resistance offered at the surface, right? For emission of heat or absorption of heat by radiation. It is given by the formula 1 minus emissivity upon area into emissivity, right? Now, A is the surface area. In convection and radiation, we take surface area because radiation is in the form of electromagnetic waves, right? From where those waves will be generated, they will be generated from the surface. So we have to take the surface area. In Stefan Boltzmann's law also, Q is equal to sigma A T1 raised to 4 minus T2 raised to 4. What A you will take? You will take A as surface area. For example, if a spherical ball is there, you will take A as 4 pi r square. If a cylindrical object is there, you will take A as pi dl because pi dl is the surface area of cylinder. In previous case, 4 pi r square is the surface area of sphere. So, is the concept of surface resistance clear to you? Surface resistance means resistance offered to the flow of heat at the surface itself, right? It is given by the formula 1 minus emissivity upon area into emissivity. The second is shape resistance. The shape resistance is offered due to shape, geometry, and orientation of the object. That shape resistance is given by the formula 1 upon area into shape factor. 1 upon area into shape factor. Shape factor is also called as view factor. Let's say the heat is flowing from 1 to 2. So what will be shape resistance? 1 upon area 1 because heat is generated from plate 1. 1 upon A1 into F12. Similarly, if heat is flowing from 1 to 3. What will be shape resistance? 1 upon A1 into F13. On the same line, if heat is flowing from plate M to plate N, shape resistance will be 1 upon AM into Fmn. That is view factor of M with respect to N. Right? Even if you are not there for the last lecture, this concept is very simple. Even if you go through the slides, you will understand. Okay, anyway, I believe that this concept is clear to you. The concept of shape resistance. It is given by the formula 1 upon A into view factor. Now see, in electrical analogy of radiation, it is similar to electrical analogy of conduction and convection. In electrical analogy of radiation, the driving potential is sigma into bracket T1 raised to 4 minus T2 raised to 4. And there are only two resistances, which are those surface resistance and shape resistance. So we'll consider this first plate, heat transfer between two infinite parallel plates. Now see, two plates are there. This is plate 1 and this is plate 2. T1 is the absolute temperature. As I told you in the first lecture itself, we have to take absolute temperatures in case of radiation, right? T1 is the absolute temperature. Absolute temperature is given in Kelvin. T1 is the absolute temperature of plate 1. Epsilon 1 is the emissivity of plate 1. T2 is the absolute temperature of plate 2. Epsilon 2 is the emissivity of plate 2. Now what we have to find? We have to find how much heat is flowing from plate 1 to plate 2. How much heat is flowing? What is the heat transfer rate by radiation from plate 1 to plate 2? So this case is of two parallel plates, two parallel infinite plates. Their lengths are infinite, right? Okay. Now see, when heat will flow from 1 to 2, what will be first resistance? The first resistance will be offered at the first plate itself. It will be resistance offered to emission of heat that we call as surface resistance, right? So R1 is what? R1 is surface resistance of plate 1. If 1000 watts energy is given to plate 1, it cannot emit all 1000 watts. There will be some resistance which will be offered at the plate itself. That resistance is called as surface resistance. Now let's say 1000 watts is the input given to plate 1, out of which it is not able to emit 1000 watts. Let's say it emits 900 watts. Now this 900 watts is moving from plate 1 to plate 2. Now out of 900 watts, all energy emitted by 1 will not reach up to 2, no? So there will be shape resistance. There will be shape resistance, right? What is the formula for shape resistance? 1 upon area into shape factor. That we'll discuss later on. This is R2. What is R2? R2 is the shape resistance of plate 1 with respect to 2. Let's say out of this 900 watts, only 800 watt will reach up to plate 2, right? Now, if that 800 watt is incident on plate 2, can plate 2 absorb all 800 watts? Obviously, the answer is no. It cannot absorb all 800 watts because there will be some resistance for absorption of heat. That resistance is also called as surface resistance. So there will be three resistances, R1, R2 and R3. What is R1? Surface resistance of plate 1. What is R2? Shape resistance of plate 1 with respect to 2. And what is R3? Surface resistance of plate 2. See, the formulas or the derivations or everything is very simple. Only thing is that the same concept is applied everywhere. Even if here there is plate 3, again there will be 3 resistances, right? Okay. So first resistance is R1. What is R1? Surface resistance of plate 1. R2 is shape resistance. And what is R3? Surface resistance of plate 3. I will give you a simple example. Let's say I am teaching to you, right? Let's say I have to deliver in today's session, I have to cover 10 concepts, right? Now see, how many resistances will be there in this case? The energy, like energy is nothing but concepts. They will flow from me to you. They will flow from teacher to a student. Now teacher, is he in a position to explain all 10 concepts very nicely? No. He is having some resistance. He is having some teaching efficiency. So he will explain, he will be in a position, let's say a very good teacher is there. So out of 10, he will explain 9 concepts very properly. So that is nothing but R1. Now, 9 concepts he has delivered properly. But has the student listened to all 9 concepts very properly? No. So there will be shape resistance. Out of the 9 concepts delivered, let's say the student has listened to only 6 concepts, right? In online teaching, this view factor is drastically reduced, right? Okay. So that resistance is called as shape resistance. So first resistance was teacher's resistance. He was not in a position to explain all concepts properly. Second resistance was that the teacher has explained 9 concepts, but the student has listened to only 6 concepts. Now, the student has listened to 6 concepts, but is he an ideal student that he has listened to 6 concepts and all 6 concepts are clear to him? No. There will be some resistance in his absorption, right? So that resistance is also called as surface resistance. So out of 6, let's say he has understood only 4 concepts. So 10 concepts were delivered or were supposed to be delivered, out of which only 4 concepts were understood, right? So which 3 resistances will be there? Emission resistance, right? Shape resistance and absorption resistance. Emission resistance and absorption resistance, they are called as surface resistances. And this shape resistance is called as shape resistance. Surface resistance is given by the formula 1 minus emissivity upon area into emissivity. And shape resistance is given by the formula 1 upon area into shape factor, right? So in this case, tell me what will be R1? R1 will be 1 minus emissivity upon area into emissivity. Now what is emissivity of plate 1? It is epsilon 1. What is area of plate 1? It is A1. So it will be 1 minus epsilon 1 divided by A1 epsilon 1. This will be your R1, 1 minus epsilon 1 upon A1 epsilon 1, right? Now, tell me what will be R3? R3 is surface resistance of plate 2. As I have told you that surface resistance is 1 minus emissivity upon area into emissivity. Here area is A2 and emissivity is epsilon 2, right? So R3 will be equal to 1 minus epsilon 2 upon A2 into epsilon 2. What will be R3? 1 minus epsilon 2 upon A2 into epsilon 2, right? And what is R2? Shape resistance. Shape resistance is given by the formula 1 upon area into view factor. It will be 1 upon A1 into F12. It will be 1 upon A1 into F12 because heat is flowing from 1 to 2. So we have to consider a view factor of 1 with respect to 2. Right? Now, what is the driving potential? The driving potential in radiation is sigma into bracket T1 raised to 4 minus T2 raised to 4. In electrical circuits, we call this factor as voltage. Right? Okay. The driving potential in case of radiation, heat transfer by radiation is sigma into bracket T1 raised to 4 minus T2 raised to 4, where T1 and T2 are absolute temperatures. Sigma is Stefan Boltzmann's constant. I believe that it is clear to you. So driving potential is sigma into bracket T1 raised to 4 minus T2 raised to 4, and there will be 3 resistances. How will you find Q? The concept is very simple. In electrical circuits, we say I is equal to V upon R. Current is equal to potential divided by resistance. Similarly, in thermal circuits, what we can say? We can say that Q is equal to potential upon resistance. Q is equal to, Q is what? Q is the rate of heat flow by radiation. It is equal to potential difference divided by all resistances. So in this case, it will be sigma into bracket T1 raised to 4 minus T2 raised to 4 upon summation R. In summation R, how many resistances are there? There are 3 resistances, R1, R2 and R3. So how can we find Q in this case? To find Q in this case, we have to apply equation QR is equal to, what is the potential? Sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by summation R. Now summation R is nothing but R1 plus R2 plus R3. What is the value of R1? R1 is surface resistance. It is given by the formula 1 minus emissivity upon area into emissivity. R2 is the shape resistance of 1 with respect to 2. 1 upon A1 into F12. What is R3? Surface resistance of plate 2. It is given by the formula 1 minus emissivity upon area into emissivity. So it is 1 minus epsilon 2 upon A2 into epsilon 2. Tell me honestly, any difficulty till this stage? If you are having any difficulty, you can unmute yourself and you can ask me the questions. Or else I will assume that the concept is clear to you. So can we proceed? So in today's session, we have started with heat transfer between two infinite plates. We have considered two infinite parallel plates having temperatures T1 and T2 and emissivities epsilon 1 and epsilon 2. Now we have to find QR. QR is nothing but the rate of heat transfer by radiation from plate 1 to plate 2, right? Now the driving potential, right? Why heat will flow? It will flow because of this factor sigma into bracket T1 raised to 4 minus T2 raised to 4, right? The driving potential is sigma into bracket T1 raised to 4 minus T2 raised to 4, where T2 and T1 and T2 are absolute temperatures. What is R1? Surface resistance offered by plate 1. What is R2? Shape resistance. What is R3? Surface resistance offered by plate 2. What is R1? 1 minus epsilon 1 upon A1 epsilon 1. I repeat, surface resistance is 1 minus emissivity upon area into emissivity. See, this concept is very simple. Electrical analogy of radiation. Just you have to remember two formulas. Which are those? One is surface resistance and another one is shape resistance. You can work out any numerical in the universe where radiation is taking place. Just you have to consider only two resistances, and those two formulas are also very small. They are very simple. They are very easy to memorize. Surface resistance is given by the formula 1 minus emissivity upon area into emissivity, and shape resistance is given by the formula 1 divided by area into shape factor or area into view factor. So in this case, if I want to find QR, I will use the simple concept current is equal to potential upon resistance. Simply I will write QR is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by R1 plus R2 plus R3. So I will write this. QR is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by R1 plus R2 plus R3. So it will be sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by, what is R1? 1 minus epsilon 1 upon A1 epsilon 1. What is R2? 1 upon A1 F12. And what is R3? 1 minus epsilon 2 upon A2 epsilon 2. Now, as the plates are infinite, their areas will be same. As the plates are infinite, A1 and A2 will be equal to A. Now, as the plates are infinite, view factor of 1 with respect to 2 will be 1. All energy emitted by 1 will be directed towards 2. So view factor will be 1. Now see, what will be the formula for QR now? It is sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by. Now A, I have taken it outside because A1, here A1 was there, here A1 was there and here A2 was there. But A1 and A2, they are same. So I have taken A outside the bracket. So it is 1 upon A into bracket 1 minus epsilon 1 upon epsilon 1 plus 1 upon F12 plus 1 minus epsilon 2 upon epsilon 2, right? Now what is this F12? F12 is again 1. Now see this A, it will come in the numerator. So what will be the formula? The formula will be sigma into bracket T1 raised to 4 minus T2 raised to 4 into A divided by, now see denominator. What will be there in the denominator? 1 upon epsilon 1 minus 1. Is the first term clear to you? Now F12 is 1. right? So let's write it as it is, 1 upon F12. And what will be this term? 1 upon epsilon 2 minus 1. Now, that F12 is 1. So minus 1 plus 1, it will get cancelled, right? And what will be left in the denominator? In the denominator, what will be left? 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. So what will be formula for QR? It will be sigma A into bracket T1 raised to 4 minus T2 raised to 4 divided by 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. So if you take A on this side, if you take A on left hand side, what will be the formula? The formula will be QR upon A is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. This is the final formula. This simple formula you have to memorize to solve the numericals where electrical analogy of radiation is to be applied. If you want to find how much heat is flowing by radiation from plate 1 to 2, which formula you have to apply? You have to apply the formula QR upon A is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. What is T1 and T2? T1 and T2 are absolute temperatures of plate 1 and 2. What is sigma? Sigma is Stefan Boltzmann's constant. It is given by the formula 5.67 into 10 raised to minus 8. Rather than formula, I will say its value. The value of Stefan Boltzmann's constant is 5.67 into 10 to the power minus 8. Right? Now, what are epsilon 1 and epsilon 2? They are emissivities of surfaces 1 and 2. So how will you find heat flow rate by radiation between two surfaces? We'll find the heat flow rate by radiation between two surfaces using this formula. QR upon A is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. Is it clear to all of you? If it is clear to all of you, we can work out a numerical based on this. See, as far as theory exam is concerned, when subjective exam was there, either the derivation will be asked or there will be numericals which are based on this. This derivation is very simple. Just 2 to 3 steps are there. I will just repeat the derivation. What we have done, we were supposed to find heat transfer by radiation between two infinite plates. T1 and epsilon 1 are temperature and emissivity of plate 1. Similarly, T2 and epsilon 2 is temperature and emissivity of plate 2. Right? So we have drawn this equivalent electrical circuit. 3 resistances are there. Surface resistance of plate 1, shape resistance, surface resistance of plate 2. The driving potential is sigma into bracket T1 raised to 4 minus T2 raised to 4. Now, we have written the values of R1, R2 and R3. R1 is 1 minus epsilon 1 upon A1 epsilon 1. R3 is 1 minus epsilon 2 upon A2 epsilon 2. And R2 is 1 upon A1 F12. R2 is shape resistance. Then simply we have written QR is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by summation R. In case of electrical circuits, we write current is equal to potential upon electric resistance. Similarly, in thermal circuits, we write heat transfer rate is equal to potential difference divided by thermal resistance. In this case, there are 3 thermal resistances, right? So QR is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by summation R. Summation R is equal to R1 plus R2 plus R3. What is R1? 1 minus epsilon 1 upon A1 epsilon 1. What is R2? 1 upon A1 F12. What is R3? 1 minus epsilon 2 upon A2 epsilon 2. So simply we have taken A as common because A was same. A1 is equal to A2 is equal to A. Why they are same? Because the plates are infinite. Infinite means they are same. We cannot measure them. So by default, they are same. A1 is equal to A2 is equal to A. And now see, plate 1 is facing plate 2 and they are parallel and they are infinite. So all energy emitted by 1 will be directed towards 2. So view factor of 1 with respect to 2 will be equal to 1. So in this last stage, if we substitute F12 is equal to 1, this minus 1 and plus 1 will get cancelled, and finally we'll get this expression QR upon A is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by 1 upon emissivity of plate 1 plus 1 upon emissivity of plate 2 minus 1. Tell me very honestly, is this derivation clear to you? I will just repeat the final step. The heat flux, the radiant heat flux between two infinite parallel plates is given by the expression sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. Okay. So if you are having notebook and pen, you can write down this numerical, right? Okay. Now I will just read out the numerical for you. What is given in this numerical? There are two parallel plates. Large means we have to assume that the plates are infinite. Two large parallel plates of emissivity is 0.1 and 0.05. So which value is given? Emissivity of plate 1 and emissivity of plate 2. So it is nothing but epsilon 1 and epsilon 2. So in this case, epsilon 1 is given as 0.1. Epsilon 2 is given as 0.05, right? And are at absolute temperatures of 350 Kelvin and 300 Kelvin. So the plate temperatures are given. Plate temperatures, we denote them. We call them by temperatures T1 and T2. So T1 is given as 350 Kelvin and T2 is given as 300 Kelvin. They are situated 2.5 millimeter apart. Now we have seen the derivation. There is no question of distance, right? It is just given to mislead you, but we should not get misled. All given data may not be useful, right? So we need only four values and they are given. Which values we need? We need the values of epsilon 1, epsilon 2 and T1 and T2. In this case, epsilon 1 is given as 0.1, epsilon 2 is given as 0.05, T1 is given as 350 and T2 is given as 300. What we have to find? We have to find QR, heat transfer rate by radiation per unit area. What is the formula that we are having? We are having this formula. QR upon A is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. You know sigma is 5.67 into 10 to the power minus 8. I have told you in the first lecture, I have repeated in second lecture also, and now also I am repeating that the value of sigma is 5.67 into 10 to the power minus 8. It is in sequence 5, 6, 7, 8. 5.67 into 10 raised to minus 8. Okay, you can put the values of T1, T2, epsilon 1, epsilon 2, and we can find radiant heat flux. So just work out and tell me what answer you are getting. I will just wait for 2 minutes. Meantime, you can work out the calculations. Very simple calculations are there. QR upon A is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by 1 upon emissivity of plate 1 plus 1 upon emissivity of plate 2 minus 1. Now remember that you have to take T1 and T2 in Kelvin. In radiation, we have to take temperatures in Kelvin. Earlier we have discussed in conduction and convection, we deal with temperature difference. In radiation, we deal with absolute temperature. Stephen Boltzmann law says that the emissive power of a black body is directly proportional to fourth power of its absolute temperatures. So remember that in radiation, we have to take temperatures in Kelvin. Here the temperatures are given in Kelvin, but in some of the numericals, the temperatures are given in degrees Celsius. So over there, you have to add 273 and you have to convert the temperatures into degree Kelvin. I believe that your calculations are over. If you do the calculations, you will find that QR upon A is equal to 13.5 watts per meter square, right? Okay. So I believe that this concept is clear to you. What was the first concept? Heat transfer by radiation between two infinite parallel plates, right? Okay. So can we start with the next point? Please write in the chat box. Can we start with the next point? Okay. So we'll start with the next point. Heat transfer by radiation between two parallel plates. Only what is the difference? In the second case, one shield is added. One more plate is placed in between 1 and 2. Now this is called as radiation shield. Why that shield is used? What is the purpose of using radiation shields? It is to reduce the heat loss, right? Radiation shields are used to reduce the heat loss. See, being an engineer, we may be asked to design the radiation shields so that the heat loss should be reduced. Let's say a boiler furnace wall is there. There the temperatures are very high. So heat loss is because of radiation. So in that case, you have to design shields. right? You may be supposed to find how many number of shields are required, or what should be the emissivity of shields, right? Okay, so this is the case of two parallel plates where in between the two parallel plates, one more plate is placed. That plate is called as shield. Now I will look at this figure mathematically, right? So in this case, three plates are there, right? This was my plate 1 and the last one is plate 2. It is similar to the first one, right? 1 and 2, T1 epsilon 1, T2 epsilon 2. Now in between 1 and 2, one more plate is placed. That let us call that plate as plate number 3, right? On the extreme left side, you are having plate number 1. On the extreme right side, you are having plate number 2. This is similar to previous case, two infinite parallel plates. Only what is the difference? The difference is that in between these two plates, one more plate is placed, right? It is placed at the center, or let's say it is placed at the middle of the arrangement. Let's say that, let's call that plate as plate number 3. It is not necessary that we should call them as 1, 2, 3. It may be in sequence like 1 is at the left, 2 is at the center, 3 is at the right. But for the sake of simplicity, comparing it to the previous case, I have mentioned that plate on the left side is 1, plate on the right side is 2, and the center plate is 3. So T1 and T1, T2, T3 are the absolute temperatures, epsilon 1, epsilon 2, epsilon 3 are the emissivities. Now, as the plates are infinite, I can say that A1 is equal to A2 is equal to A3, that is equal to A. As the plates are infinite, shape factor of 1 with respect to 3 will be 1. Shape factor of 3 with respect to 2, it will be 1. I repeat, as the plates are infinite, their areas must be same. I can say that A1 is equal to A2 is equal to A3, right? As the plates are infinite and parallel, view factor of 1 with respect to 3 or view factor of 3 with respect to 2 will be same. Now how heat will flow in this case? In previous case, heat was directly flowing from 1 to 2. Now heat will flow from 1 to 3 and then it will flow from 3 to 2. Now when heat will be flowing from 1 to 3, how many resistances will be there? There will be 3 resistances, right? Again, when the heat will flow from 3 to 2, how many resistances will be there? Again, there will be 3 resistances, right? Now, let us consider the first case. When heat is flowing from T1 to T3, there will be 3 resistances, R1, R2, and R3. What is the first resistance? Surface resistance of plate 1. Then shape resistance of plate 1 with respect to 3. Next, surface resistance of plate 3. Are you getting? When heat will flow from 1 to 3, there will be 3 resistances. Surface resistance of plate 1, shape resistance of plate 1 with respect to 3, and surface resistance of plate 3. Now, energy, radiant energy has reached up to plate 3. Now, the heat will flow from 3 to 2. Again, how many resistances will be there? Again, there will be 3 resistances, right? Surface resistance of plate 3, shape resistance of plate 3 with respect to 2, and surface resistance of plate 2, right? So totally there will be 6 resistances. Okay, can anyone tell me? Now see, I think the arrangement is clear to you. This is equivalent electrical circuit. Now if the question is for 8 marks, 2 marks are there when you draw this equivalent electrical circuits. Now what will be driving potential? The energy is ultimately flowing from 1 to 2. So the potential because of which, the potential difference because of which this heat is flowing is sigma into bracket T1 raised to 4 minus T2 raised to 4. Now when this heat is flowing, right, how many resistances are offered to that flow of heat? There are 6 resistances which are offered to the flow of heat. I repeat, which are the resistances? Surface resistance of plate 1, shape resistance of plate 1 with respect to 3, surface resistance of plate 3, then again surface resistance of plate 3, shape resistance of plate 3 with respect to 2, and surface resistance of plate 2. Okay. So, as I told you, there are only 2 resistances. One is surface and one is shape. What is the formula for surface resistance? It is 1 minus emissivity upon area into emissivity. Now, can anyone tell me what will be value of R1? R1 will be 1 minus epsilon 1 upon A1 epsilon 1. Right? Now, what is R2? shape resistance of 1 with respect to 3. What is the value of shape resistance? 1 upon area into shape factor. So it will be 1 upon A1 F13. Right? Now, what will be R3? R3 is surface resistance. It is 1 minus, yes, what will be R3? 1 minus emissivity upon area into emissivity. Right? The emissivity is epsilon 3. So it is 1 minus epsilon 3 upon A3 epsilon 3. Similarly, R4, 1 minus epsilon 3 upon A3 epsilon 3. R5. R5 is shape resistance of plate 3 with respect to 2. What will be R5? 1 upon area into view factor. So what is area? Area is A3. Heat is flowing from 3 to 2. So view factor of 3 with respect to 2. So it is 1 upon A3 F32. And what will be R6? 1 minus epsilon 2 upon A2 epsilon 2. So these are the values of resistances. Now I will repeat. What is R1? 1 minus epsilon 1 upon A1 epsilon 1. Right? R1 is where? R1 is resistance offered at the plate itself, first plate itself. What is R2? Shape resistance of plate 1 with respect to 3. So what is the formula for shape resistance? 1 upon area into shape factor. Now 1 with respect to 3. So F will be F13, 1 with respect to 3. And as it is emitted by 1, it will be A1. Right? Now what is R3? Surface resistance of plate 3 on the left side. Right? Now, what is surface resistance? 1 minus emissivity upon area into emissivity. Now, which plate is this? Plate number 3. So 1 minus emissivity of plate 3 upon area of plate 3 into emissivity of plate 3. So what will be the formula? 1 minus epsilon 3 upon A3 epsilon 3. I believe that you are getting the concepts. I believe that the things are clear to you. There are two resistances. One is surface resistance and one is shape resistance. Surface resistance is given by the formula 1 minus emissivity upon area into emissivity. And shape resistance is given by the formula 1 upon area into view factor. Now, if heat is emitted by 1 and if it is going up to 3, then we have to write 1 upon A1 F13. Okay. What is R4? Now see, R4, R5, R6 are the resistances which are offered when the heat flows from 3 to 2. Right? So what is R4? Surface resistance of plate 3. What is R5? Shape resistance of plate 3 with respect to 2. And what is R6? Surface resistance of plate 2. Now, what is R4? Surface resistance of plate 3. Now, what is the formula for surface resistance? It is 1 minus emissivity upon area into emissivity. What is the number of plate? Which plate is this? Plate number 3. So 1 minus epsilon 3 upon A3 into epsilon 3. What is R5? Shape resistance of plate 3 with respect to 2. So what is the formula for shape resistance? It is 1 divided by area into view factor. Now area is 3 and heat is emitted from 3 up to 2. So the view factor will be F32. Right? See, even if you don't know the concept of shape factor in electrical analogy of radiation, there will not be much problem. Why? Because in this case, the case of heat transfer between parallel plates, the shape factor is always 1. Right? Because all energy emitted by 1 if the surfaces are infinite and if they are parallel. Right? Shape resistance depends on what? Geometry, shape and orientation. What is the orientation in this case? They are parallel. Right? What is the geometry? They are rectangular plates. Right? And they are infinite. So all energy emitted by one will be intercepted by the other. So even if you don't know the concept, even if you don't have attended the last lecture of view factor or shape factor, still you can manage this thing. Right? Okay. What is last resistance? R6, surface resistance of plate 2. It is given by which formula? 1 minus emissivity upon area into emissivity. The plate number is 2. So what will be the formula? 1 minus epsilon 2 upon A2 epsilon 2. I believe that it is clear to you. Now see, which equation we write in electrical analogy? We write the equation current is equal to potential upon resistance. In heat circuits, we write heat flow rate is equal to driving potential divided by resistance. Now, what is the current or what is heat? Heat is nothing but QR. What is the driving potential in radiation? It is sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by resistances. Now we have seen that if two parallel plates are there, right, there will be only 3 resistances. But if one shield or if any one plate is placed in between two plates, there will be totally 6 resistances, R1 to R6. So in this case, the formula will be QR is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by R1 plus R2 plus R3 plus R4 plus R5 plus R6. Now simply I have written the values of R1, R2, R3, R4, R5 and R6. What is the value of R1? 1 minus epsilon 1 upon A1 epsilon 1. What is the value of R2? 1 upon A1 F13. What is the value of R3? 1 minus epsilon 3 upon A3 epsilon 3. What is the value of R4? 1 minus epsilon 3 upon A3 epsilon 3. What is the value of R5? 1 upon A3 F32. And what is the value of R6? 1 minus epsilon 2 upon A2 epsilon 2. So simply I have written those values. Now, what will be next step? In next step, I will substitute that these view factors F13 and F32, they are 1. And A1 is equal to A3 is equal to A2. The areas are same as the plates are infinite. I can say that A1 is equal to A2 is equal to A3, that is equal to A. As the plates are infinite, also I can say that the view factors are unity. So simply I have substituted those values, right? And what I will get, sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by this. Now see, 1 minus epsilon 1 upon epsilon 1. So what it will be? 1 upon epsilon 1 minus 1, right? Now this term, what is this term? 1 upon A1 F13. F13 is 1, right? And A you have taken outside, so it will be plus 1. So if you do simple mathematics, some plus 1 minus 1 will get cancelled. And what is the final expression we get? The final expression what we get is QR upon A is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1, right? Plus this additional bracket we get. This is 1 upon epsilon 3 and again 1 upon epsilon 3. So 1 upon epsilon 3 plus 1 upon epsilon 3 is 2 upon epsilon 3. So it is 2 upon epsilon 3 minus 1. So this additional bracket just you have to memorize. This formula already we have memorized. This formula QR upon A is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. This already we have memorized, right? What additional thing we have to remember? If we are using a shield, one more factor will be there. And what is that factor? That factor is nothing but 2 upon epsilon 3 minus 1, right? Why that 2 term is there? Because that shield is having two sides which are effective, which will come into existence, which will come into play, right? So it is 2 upon epsilon 3 minus 1. Is it clear to you? Okay, please just write down this formula. There are two formulas. Which are those? First formula is this. When there are no shields, what is the formula? QR upon A is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1, right? And if shield is there, we will write this in bracket and we'll add one more bracket in the denominator. And what is that bracket? That bracket is 2 upon epsilon 3 minus 1. What is epsilon 3? Emissivity of the shield. See, 1 and 2 are the plates and 3 number is nothing but shield which is placed in between plates 1 and 2. So is it clear to you? If you have written the formula, we will work out a numerical which is based on this. Please write down the formula. A, either you can write it over here or also you can take A in the left hand side, so that the left hand side will be QR upon A. So what expression we will get? QR upon A is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by this bracket 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1 plus second bracket is 2 upon epsilon 3 minus 1. So please write down this numerical. We'll work out one more numerical. I believe that the screen is visible to you. And also I will read out the numerical for you. Okay. I will just read out the numerical for you. Find out heat transfer rate per unit area due to radiation between two infinite parallel long plates. Now same case is there. Two infinite parallel long plates. The first plate has emissivity of 0.4 and is maintained at 200 degrees Celsius. Okay, even if you don't write the numerical, on next slide I have just directly written the given data. Okay, so what is given in this case? The first plate has emissivity 0.4, means what is the given data? Epsilon 1, first plate we call it as 1, second plate we call it as 2. T1 and epsilon 1 are the temperature and emissivity of plate 1. Now what is the temperature of plate 1? T1. T1 is 473, right? What is epsilon 1? 0.4. Emissivity of the second plate is 0.2 and it is maintained at 30 degrees Celsius. 30 degrees Celsius means 303 Kelvin. So what is given? Epsilon 2 and T2 is given. Epsilon 2 is given as 0.2. T2 is given as 303. So please write down that epsilon 2, T2. Now, a radiation shield having emissivity 0.5 is placed between the plates. Now we call that plate which is placed in between 1 and 2 as 3. So epsilon 3 is given as 0.5. What we have to find? Percentage reduction in heat transfer rate due to radiation shield, and also find the temperature, steady state temperature attained by the shield. Now see, this is the case. See, being engineer, we have to find this, that if we introduce a shield, how much percentage reduction will be there in the heat loss or heat transfer rate, right? Okay, now in this case, what is given? T1 is given, T2 is given, T1 epsilon 1, T2 epsilon 2, T1 is given as 473 Kelvin, epsilon 1 is given as 0.5, T2 is given as 303, epsilon 2 is given as 0.2, and this is the third plate. It is having emissivity 0.5. So epsilon 3 is given as 0.5, right? Now, what we have to find? We have to find that how much reduction is there in the heat transfer rate due to this shield. Just assume that without shield, when no shield was there, if no shield is present over there, let's say that the heat loss rate is 100 watts per meter square, right? And when shield is placed, let's say that the heat loss rate is 60, right? So how much will be percentage reduction? It will be 100 minus 60 upon 100. So it will be 40%, right? So what we have to calculate in this case? We have to calculate the heat transfer rate without shield and heat transfer rate with shield, right? Now, without shield, what formula will apply? The formula which I have written at the bottom, right? What is the formula without shield? QR upon A is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. This is the formula which we will use when there is no shield. If there is shield, which formula we use? We use the formula QR upon A is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. This term is as it is, right? The two equations are same, only this term is additional. What is that term? Plus 2 upon epsilon 3 minus 1, right? So what we will work out? We will work out the rate of heat flow by radiation without shield when shield was not there, and we will work out the rate of heat loss by radiation when shield was there, right? It is obvious that when you place shield, the rate of heat transfer will get reduced. Now see, if you do the calculations, now see, is the question clear to you? See, in the first step, you have to write given data. You have to draw the diagram. I have drawn simple 2D sketch. In fact, you will also have to draw this simple 2D sketch. There are two plates, 1 and 2, and third plate is placed in between plates 1 and 2. T1 is given, T2 is given, epsilon 1 is given, epsilon 2 is given, and epsilon 3 is given, right? Now, what we have to find? Heat transfer rate with shield and heat transfer rate without shield. Now, if you calculate heat transfer rate with shield, you will use this formula and the figure will come out to be 248.44 watts per meter square. If you calculate heat transfer rate without shield, it will come out to be 363.1. And how will you calculate percentage reduction? It will be heat transfer rate without shield percentage reduction in heat transfer is equal to heat transfer rate without shield minus heat transfer rate with shield divided by heat transfer rate without shield. See, I have written this formula. Percentage reduction is equal to Q without heat shield minus Q with heat shield divided by Q without heat shield. So you can calculate the percentage reduction. Okay, so if you calculate that, you will get how much is the percentage reduction. Now next point is that we have to find T3. Now see, when you have to find T3, temperature of shield, generally it is not asked to find temperature of shield, but if it is asked, how will you find temperature of the shield? Now just consider that heat is flowing from 1 to 3. Now when heat is flowing from 1 to 3, what formula I can write? QR upon A is equal to sigma into bracket T1 raised to 4 minus T3 raised to 4 divided by 1 upon epsilon 1 plus 1 upon epsilon 3 minus 1. I'm not considering plate 2. I'm just considering heat transfer between plates 1 and 3. Right? Also, you can cross check your answer. Now see, in this case, this QR upon A already you have calculated. You know the value of epsilon 1 and epsilon 3. You know the value of sigma. You know the value of T1. So you can calculate T3. How can I cross check my answer? Similarly, I can use the formula that heat is flowing between 3 and 2. So what equation I can write? QR upon A is equal to sigma into bracket T3 raised to 4 minus T2 raised to 4 divided by 1 upon epsilon 3 plus 1 upon epsilon 2 minus 1. Simply if I use that formula, right, by that also I can calculate T3. So in these numericals also you can cross check your answers. Okay, tell me, is it clear to you? Are you getting? Or else what will happen that I will go on explaining and at the end of session I will come to know that you have not understood anything. Tell me honestly, is it clear to you? We'll just brush up what we have studied till now and then we'll decide whether to go ahead or to what extent you have understood the concept. See, in this lecture we have started with electrical analogy of radiation. In conduction, you have seen electrical analogy of conduction. Different resistances are there. For example, let's say conduction plus convection is there and the numerical is of slab. Then you know that the conductive resistance of slab is B upon K. The convective resistance is 1 upon HA. Or if cylindrical system is there, let's say a pipe is there which is insulated. In that case, that conductive resistance is ln of R2 by R1 upon 2 pi KL. The convective resistance on inside is 1 upon HI AI, where AI will be equal to 2 pi RL. The convective resistance on outer side will be 1 upon HOAO, right? Now, if the system is spherical, the conductive resistances will be outer radius minus inner radius upon 4 pi K and the product of outer radius and inner radius. Let's say if the radii are R1 and R2 and conductivity is K, then it will be R2 minus R1 upon 4 pi K R1 R2, right? So similarly in radiation, just you have to remember only two formulas. Which are the two formulas? One is surface resistance and one is shape resistance. What is surface resistance? Surface resistance is the heat resistance offered to the flow of heat by radiation at the surface itself. It may be the resistance offered to emission of energy or it may be the resistance offered to absorption of energy. It is given by the formula 1 minus emissivity upon area into emissivity. It is 1 minus epsilon upon A into epsilon. I believe that it is clear to you. Surface resistance is 1 minus emissivity upon area into emissivity. What is shape resistance? It is the resistance offered due to geometry, shape and orientation of the objects. It is given by the formula 1 upon area into view factor. It is given by the formula 1 upon area into view factor. Let's say heat is flowing from 1 to 2, right? As heat is emitted by 1, I have to consider area of plate 1. As it is emitted by 1 and moving towards 2, I have to consider view factor of 1 with respect to 2. View factor and shape factor are one and the same. These are the two terminologies, right? View factor is also called as shape factor. In some of the books, it is called as shape factor. In some of the books, it is called as view factor. In last lecture, we have seen view factor. Also, we have seen the laws regarding view factor. What is view factor? Fraction of energy emitted by one which is intercepted by the other. We have also seen the laws that for a flat surface and convex surface, the view factor with respect to itself is 0. For concave, it is not equal to 0. Then we have seen enclosure theorem, reciprocity theorem. What is enclosure theorem? If n number of surfaces forms an enclosure, the summation of view factors is unity. For example, if 3 surfaces are there, we can write f11 plus f12 plus f13 is equal to 1. If n surfaces are there, I can go up to f1n. Then we have seen the reciprocity theorem. If two areas are 1 and 2, the view factors are related by the equation a1 f12 is equal to a2 f21, right? Okay, then we have seen summation theorem. If there are two areas 1 and 2, out of which 2 is made up of 3 and 4, a2 is made up of 3 and 4, then we can write f12 is equal to f13 plus f14, right? Okay. Anyway, that is not required over here. Just you have to remember that the shape resistance is given by the formula 1 upon area into shape factor of 1 with respect to the other. So these two simple formulas, are they clear to you? One is surface resistance and one is shape resistance. Now, in case of electrical analogy, what is the driving potential? The driving potential is sigma into bracket T1 raised to 4 minus T2 raised to 4. And which are the resistances? The resistances are surface resistance and shape resistance. Then we have considered two cases. This is the first case that we have considered, which is this case, heat transfer between two infinite parallel plates. These are the two infinite parallel plates, right? 1 and 2 having temperatures T1 and T2, absolute temperatures T1 and T2 in Kelvin. Emissivity is epsilon 1 and epsilon 2. What we have to find? How much heat is flowing from 1 to 2 by radiation. So we have to find QR. How many resistances are there? In this case, there will be three resistances, R1, R2 and R3. What is R1? Surface resistance of plate 1. Right? What is the formula for surface resistance? 1 minus emissivity upon area into emissivity. As it is plate 1, it will be 1 minus epsilon 1 upon A1 epsilon 1. What is R2? Shape resistance of 1 with respect to 2. So it is 1 upon A1 F12. It is 1 upon A1 F12. And what is R3? Surface resistance of plate 2. So it is 1 minus emissivity upon area into emissivity. As the plate is 2, it will be 1 minus epsilon 2 upon A2 into epsilon 2. Now, simply I have written the values of R1, R2 and R3. As we have discussed, R1 is 1 minus epsilon 1 upon A1 epsilon 1. Very simple formula is there. 1 minus emissivity upon area into emissivity. As the plate is 1, it will be 1 minus epsilon 1 upon A1 epsilon 1. R3. Similar. As the plate is 2, 1 minus epsilon 2 upon A2 epsilon 2. And what is R2? Shape resistance, 1 upon area into view factor. So simply I have written that formula. QR is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by summation R. In summation R, simply I have written the values of R1, R2 and R3. After that, I have substituted a very simple thing. What is that simple thing? That simple thing is that as the plates are infinite and parallel, their areas are same. As the plates are infinite, their areas are same. It has nothing to do with parallel. As they are infinite, they have to be same. So A1 and A2, they are same. Let's say that A1 is equal to A2 is equal to A. Now, as the plates are infinite and oriented parallelly, as they are oriented parallelly, I have to say that F12 is 1. View factor of 1 with respect to 2 will be 1. Now, if you substitute this in this equation, you will get QR upon A is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by, what will be there in the denominator? 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. So you will get this. Final step, QR upon A is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. Either you will have a numerical on this case, that heat transfer between two infinite parallel plates where there is no shield, no plate is introduced between two plates. Tell me honestly, is it clear to you? Right? And after this, we have seen the second case. What is the second case? Okay, we have worked out a numerical on this case, right? Epsilon 1 was given, epsilon 2 is given, T1 is given, T2 is given. So simply we will use this formula. QR upon A is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by this. And we can work out the answer. Right. Then we have considered the second case. What was the second case? two infinite parallel plates are there, but one radiation shield is introduced in between the two plates, right? Now, in this case, there will be 6 resistances. Heat will flow from 1 to 3. When the heat is flowing from 1 to 3 resistances will be offered to the flow of heat by radiation. When heat is flowing from 3 to 2, again 3 resistances will be offered to the flow of heat by radiation. So totally 6 resistances will be there. I repeat, totally 6 resistances will be there. And how will you calculate QR in this case? QR will be equal to driving potential upon resistances. So QR is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by R1 plus R2. We have to go up to R6. Right? So these are the values of resistances. As I had told you, even if it looks the lengthier, it is not lengthier, only two simple formulas are there. Which are those? 1 minus emissivity upon area into emissivity and 1 upon area into shape factor. So simply if you substitute that, and after this what you will substitute? Again the same substitution is there. As the plates are infinite, their areas must be same. So as the plates are infinite, A1 is equal to A2 is equal to A3 is equal to A1, A2, A3. All areas will be same because they are infinite. Now, as the plates are infinite and as they are placed parallel, the view factors or shape factors will be 1. So whichever shape factors are there, in this case we are having two shape factors, F13 and F32, both are 1. If you substitute that, finally you will get this step. What step you will get? QR upon A is equal to sigma into bracket T1 raised to 4 minus T2 raised to 4 divided by first bracket. See, the first bracket is same. Even if no shield is there, you will get this first bracket. What is the first bracket? 1 upon epsilon 1 plus 1 upon epsilon 2 minus 1. Plus you will get one additional term, which is that 2 upon epsilon 3 minus 1. So if the numerical is on shield, in that case you have to apply this formula. To work out the numerical, you have to remember this formula. So is it clear to you? And we have worked out this numerical. The two plates are there and a shield is placed in between the two plates. The emissivity of shield is given, temperatures and emissivity of plates are given, right? What we have to work out, what we were supposed to find in this numerical, we were supposed to find that because of this shield, how much is the percentage reduction in heat transfer rate? I repeat, because of this shield, how much is the percentage reduction in heat transfer rate? So how we have calculated? We have considered two arrangements. One is without shield and one is with shield. Now without shield, we know the formula, right? And also we know the formula with shield. So simply we have calculated the heat flux without shield and heat flux with shield, right? And how we have calculated the percentage reduction? Percentage reduction is Q without heat shield minus Q with heat shield divided by Q without heat shield. Using this, we have calculated the percentage reduction. Then the second task, second part of the question was that we were supposed to find shield temperature. So how we have calculated the shield temperature? We have calculated the shield temperature using electrical analogy from 1 to 3. If I apply electrical analogy from 1 to 3, what I can write? QR upon A is equal to sigma into bracket T1 raised to 4 minus T3 raised to 4 divided by 1 upon epsilon 1 plus 1 upon epsilon 2 3 minus 1. I can also cross check my answer. How can I cross check my answer? I have to write equation QR upon A is equal to sigma into bracket T3 raised to 4 minus T2 raised to 4 divided by 1 upon epsilon 3 plus 1 upon epsilon 2 minus 1. Okay. Some more numericals are there, but I think we will work out this numerical in the next lecture. So if you are having any questions, please feel free to ask the questions. Yes, are you having any questions? Please write in the chat box. Okay. Bapu Sahib Patil is saying that no questions are there. So when no questions are there, it is assumed that everything is clear to everyone. Or the second thing is that nothing is clear to anyone. So please tell me frankly, is it okay, or if you want to repetition of anything, maybe need not be in this lecture, maybe in next lecture we'll repeat that part. But tell me frankly, have you understood the concept of electrical analogy of radiation? Okay, fine. So you can give the attendance. Please write your roll numbers and then you can leave the meeting.